Now let me try to make an attempt to develop intuition behind hypothesis testing. Okay, through an example. Let's say the government of India comes out with a new coin, and and you toss a number of those coins, and you get this feeling that this coin is tail biased. Okay, now there's a difference. Tail here, I'm using the current word tail bias to mean that it's biased towards getting more tails, not in this sense, tail of a distribution. Okay, now let's say you want to prove this scientifically, statistically. How do you do that? The first thing would be you take a few coins and you toss them. Okay, step one. And toss them and note down number of tails. Okay, or this is step two. Note down, let's say, proportion of tails. How many tails have you got? Now what do you do? Step 3. Okay. Now assuming that the coin is not biased and you make 100 tosses, one would expect the data to be something like this: 50, 60, 70, 80, 40, 30, 20. Okay, these are tails obtained in a toss of 100 coins. If the coin is not biased, if it's actually a fair coin, what would we expect? We would expect something like this. Okay. Okay. I've tried to make it look like a normal distribution. Okay. One would expect something like this. Then on the vertical axis we would have the probability of obtaining like this. Okay. Now more generally we can just label the axis not as actual but as proportion. So this would be zero 0.5, 0 0.6, 0 0.7, 0 0.4, 0 0.3, 0 0.2. Okay. Now the ideal circumstances, if we toss 100 coin, okay, we should get the proportion 0.5, but since this is a statistical experiment and then randomness, there is no certainty that we're going to end up here. Okay, but if we end up not here but here, do we say that the coin is necessarily biased? Okay, now any sane person, logical person would say that it's not necessarily to be here, but it's not all that weird to obtain 60 tails in a toss of 100. But what if you get here? Okay, let's say this is 60 tails in sample. Okay, so one may say fine, it's not 50, but we don't have enough evidence to say that this is tail biased. What if it turns out to be 80 tails in sample? Then things would start to look fishy. It's a little awkward to have a fair coin, toss it 100 times and get 80 tails out of those 100. Okay, now if we have to take a call on whether the coin is actually biased or not, and we get some figures from data, we necessarily have to draw a cutoff. Okay, maybe here, or even 75 would look a little weird. Maybe on 70. That till 70 is fine. We don't have enough evidence, but if it's beyond 70, then things are fishy. Then we may infer. The keyword here is infer. We may infer that the coin is tail biased. It's biased towards getting more tails. This is the crux of hypothesis testing. Okay, the hypothesis here, roughly speaking, is whether the proportion of tails is equal to 0.5 or not, the true proportion. Okay, and the alternate here is one-tailed, because we are starting with the question is whether it's tail biased or not. Okay, so we're only going to look towards the right tail of this. Then we draw a cutoff, which is a critical value. If we take a sample and the value that we get for the proportion in the sample is towards the right of critical value, then we have evidence against null hypothesis. Okay, now let's get to terminology. Okay, and this is statistical inference. Nothing is ever proved. We only infer. The attempt that I am making here is, it's very easy to study this stuff, not do it for some time and forget it. Okay, the attempt here is that you should be able to remember this example, and through this example you should be able to remember this concept. Okay, so terminology. We have null hypothesis, okay, denoted as capital H with a subscript 0. Okay. In the particular example that we just took, if we denote theta as the true proportion of tails, on a number of tosses of the coin. This is equal to 0.5. Then we have an alternate hypothesis. In our particular example, the feeling that we started with, that the coin may be tail biased, so the true proportion of tails may be greater than 0.5. Okay. Now we're going to start by assuming that the true proportion is actually equal to 0.5. Okay. Now one can say that statisticians by and large are generally pessimistic. Okay. We're testing if the coin is actually biased. So what we're starting with, we're assuming that it's not biased. Okay. This will be every case of hypothesis testing. If we're looking for evidence for something, we're going to start with the assumption that it's not true. The other case is true. And then we're going to look for evidence. Okay. So null hypothesis here would be our target. We're going to target this. If this is not true, we're going to assume this is going to be true, and then we're going to target this with data. Okay. We have critical value, the cutoff that we just discussed, and going to have rejection region. If the value that the sample throws at us is more extreme than the critical value, okay, that more extreme region is the rejection region. It will be more clear with the example. Let's say in our particular example, he said that .5. Okay, H naught was theta is equal to 0.5 and H1 was theta is greater than 0.5. Okay. Then if it's one-tailed, we're going to have a critical value. Okay. Then this red one would be the rejection region. If this is one-tailed, okay. If this is two-tailed, then what would we do? We would just alter our null hypothesis by saying that this is not equal to 0.5. It can either be greater than or less than. Then now we're not testing the question that it's tail biased. Now this is checking for bias in general. Then what do we have? We would have two critical values. And two sections of the rejection region.